Okay, so today we'll solve GET 2020 question. This is a question from real analysis. It is a question number 21. It is saying that let for n bigger than equals to 2, we define a sequence xn by this. Then we have to find that the sequence xn converges to where, and it is up to correct up to 2 decimal places. So you have to find the limit of this sequence, right? Okay, so in order to solve this is the NPTEL reference. This you can check. Okay, let's start. So sequence is given by, so xn is a sequence. This is given by 1 by 2 pi integration 0 to pi by 2 tan to the power 1 by n t dt, right? So we have to find the limit of this sequence. Suppose note that this is convergent, and suppose, so we have to find the limit of this, right? Limit n tends to infinity xn means limit n tends to infinity 1 by 2 pi 0 to pi by 2 tan 1 by n t dt. So suppose first assume that you can interchange the limit and integration. So assume this. Then what will happen? First note 1 by 2 pi, then if you interchange the limit and integration, so limit n tends to infinity tan 1 by n t dt. So assuming we can interchange this, I will explain why this we can do it or not. Limit and integral. Right. So what will happen then? If suppose and as n tends to infinity, where this will go? This will goes to 1, right? So therefore then it will become 1 by 2 pi 0 to pi by 2 dt. And if you do this integration, what will 1 by 2 pi pi by 2, so 1 by 4, right? So we'll get the limit. So if we assume that we can interchange the limit, so basically we will show that this is possible. This step here will show that this we can do it. Interchanging the limit and integral is here well defined. So interchanging the limit and integration, we need level dominated convergence theorem, right? So we will use that theorem, and using this we will prove this. So let's see why we can do this. So to interchange limit and integral, we need limit DCT, right? Dominated convergence theorem. So what it is saying that suppose fn is a measurable function, and so what is saying that let fn be a sequence of measurable functions such that each fn you can dominate it by some h, and integral over, so suppose this is a measure h is finite, then you can do this. Then limit n tends to infinity fn, you can write, you can interchange the integral and limit, right? So this is the Lebesgue dominated convergence. So we want to use this theorem. So for that we have to find AH, which is integrable, right? Whose integral is, so you have to find this. So what is the here fn? So here the sequence is 10 to the power 1 by nt, right? So here we have fn t equals to 10 to the power 1 by t, right? For t belongs to 0 to pi by 2, because the integral is 0 to pi by 2, right? At pi by 2 this is not well defined. An integral, because this does not depend on one point integral, so it is tan t is defined on 0 to pi by 2. So we want to dominate this fn t by some function h which is integrable, right? So note that how tan, and this is for n bigger than equals to 2, right? N bigger than equals to 2. So how tan t is look like? First note, so suppose this is 0 and this is pi by 2, then tan t how it will look like this, right? And at the point pi by 4 this is 1, so this is tan t. So we want to bound tan to the power 1 by nt by some integrable function. So tan t is increasing on 0 to pi by 2. Note tan t is increasing on 0 to pi by 2, and what we have extra, so 0 less than tan t, so this is less than equals to 1 for t belongs to 0 to pi by 4, right? So from 0 to pi by 4 tan t is between 0 and 1, and tan t is bigger than 1 for t belongs to pi by 4 to pi by 2, right? And so as tan t is less than equals to 1 in 0 to pi by 2, so therefore so if you take the any power, it will still less than equals to 1, therefore 0 less than tan to the power 1 by n t, which is always less than 1 for t belongs to 0 to pi by 4, right? So from 0 to pi by 4 we get that this is dominated by 1. So like this. So from 0 to pi by 4 this is dominated by function 1. And from pi by 4 to pi by 2 we have to find a function. And what will happen? So and because tan t is bigger than equals to 1, if you take some bigger power it is, so and for t belongs to pi by 4 to pi by 2, what will happen? Tan to the power mt is less than 10 to the power nt, right? For all n bigger than equals to m. Because here tan t is bigger than 1. So if you take the bigger power, it will be bigger. So therefore, so in particular, tan to the power 1 by n is always tan t is less than equals to tan to the power half t for all n bigger than equals to 2, right? So for n bigger than equals to 2, 1 by n less than 1 by 2, so this inequality true. So means we get tan to the power 1 by t, this is less than square root t or tan, right? This for all n bigger than equals to 2. So we'll take this on pi by 4 to pi by 2, we'll take this square root 2, we'll bounded it by square root. So let's define a function, then define h t, which is a function from 0 to pi by 0 comma pi by 2 to r. So h of t, it is 1 when t belongs to 0 to pi by 4, because we are bounded on 0 to pi by 4 by 1, and from pi by 4 to pi by 2 are bounded it by square root 10 t. So we have defined h. Now I have to check that this is integrable on 0 to pi by 2. Now we have to check integration 0 to pi by 2 ht is finite, right? This we have to check. So what is integration this? So integration 0 to pi by 2 ht dt. So this you can write break it into two part. From 0 to pi by 4, this is 1 plus pi by 4 to pi by 2, this is square root 10 t, right? So from 0 to pi by 1, this is fine, this is pi by 4, and this will show that this is less than, I am writing it because this is positive function from 0 to pi by 2, right? 10 t, and we will show that this integral is finite from 0 to pi by 2 square root 10 t is finite. So now we will show so we will done if we can show integration 0 to pi by 2 tan to the power half t dt is finite, because if this is finite then the integral 0 to pi by 2 ht will be finite, so we can apply Lebesgue dct, then we are done. So it's remain to prove this one, right? So let's prove this one. So for that we will use one property for beta gamma function. From there we will deduce. So for that, first note what is, so let us first recall beta and gamma functions. So this is beta function. Beta we denote it by pq. This is integration 0 to 1 v to the power p minus 1 minus v to the power q minus 1 dv. So this is pq bigger than 0. And what is gamma function? This is beta function. And what is gamma function? Gamma p. This is defined from 0 to infinity. U to the power v to the power p minus 1 e to the power minus v dv. And this is also for p bigger than 0. So this is called beta function. And this is called gamma function. And there is a relation between beta and gamma function. So what is this? We have, so this is a well-known result that beta pq is gamma p times gamma q by gamma p plus q. So this is the relation between beta and gamma function. Okay. So what is this? So if you write down the definition, 0 to 1 v to the power p minus 1 minus v to the power q minus 1 dv equals to gamma p gamma q by gamma p plus q. Okay, now here take b equals to sin square theta. Then what will happen? So dv will be 2 sin theta cos theta d theta. And let's write what will happen. Then the limit at theta equals to 0, it is v is 0, v equals to 0, theta is 0, and v equals to 1, theta is pi by 2. Then this will be 0 to pi by 2 sine to the power 2 p minus 1 theta, and 1 minus sine square, so it is cos square 2 q minus 1 theta, and it is 2 sin theta cos theta d theta. Right, so this is same as gamma p gamma q by gamma p plus q. Or if you simplify, what you will get? So 0 to pi by 2 sine to the power 2p minus 1 theta cos to the power 2q minus 1 theta d theta equals to gamma p gamma q by gamma p plus q, or 2 is here. Now again put, now take take p equals to k plus 1 by 2 and q equals to 1 minus k by 2 for k less than 1, right, because pq in it bigger than 0. So then what will become? Then 0 to pi by 2, it will become sine to the power k into cos to the power minus k theta. D theta equals to this gamma 1 plus k by 2 gamma 1 minus k by 2 by 2, it will become 1, or gamma 1 is 1. So which implies 0 to pi by 2 tan to the power k theta d theta equals to half of gamma 1 plus k by 2 into gamma 1 minus k by 2, and this is for k strictly less than 1, right? So now we need tan to the power square root tan theta, right? So put k equals to 2. So for k equals to 2, we get 0 to pi by 2 tan to the power half t dt. So this is k equals to half, right? So this is gamma half gamma 3 by 4 and gamma 1 by 4. And this you can show that this is finite. So we got 0 to pi by 2 tan to the power half dt is finite. You can explicitly find the explicit value of this. So let me also write. So there is this is well known result. It is well known that what is the relation? So gamma z gamma 1 minus z. So there is a relation between this. This is pi sine pi z for z not being integer. So for k less than half, because we have to find this one, right? So for k less than half, let's put this one. Z equals to 1 plus k by 2. Then what you will get? Gamma 1 plus k by 2 into gamma, it will become 1 minus k by 2. So it will be pi by sine 1 plus k by 2 into pi. Then what is this? If you simplify, you will get sine pi by 2 plus k pi by 2, means it is pi by cos k pi by 2. So this is pi by pi into sec k pi by 2. So you have got this. Therefore integration 0 to pi by 2 tan k t dt is pi sec k pi by 2, and putting k equals to half, we get 0 to pi by 2 10 to the power half t dt. This is pi sec pi by 4. So this is obviously finite. So therefore, so is this integral finite? Therefore integral h 0 to pi by 2 ht is also finite. So yeah, this is satisfied. So therefore we can use Lebesgue dct. Right, so DC, a condition for dct is satisfied, so we can use dct. So therefore we can interchange this limit and integral. So therefore this is fine, and we get this is 1 by 4, so this is 0.25 up to 2 decimal places. So therefore the answer is 0.25. So therefore then the sequence converges to 0. Let me write it, 0.25. Okay.